Hello everyone, I am Karan Mashru. Welcome to this video. In this video, we are going to discuss solution of the problem of the day, that is floor in BST. First of all, let us start by understanding the question. You are given a BST binary search tree with n number of nodes and value x. Your task is to find the greatest value node of the BST which is smaller than or equal to x. So basically, we are given a binary search tree where there are n nodes. Each node has a value associated with it, and out of all the values which are less than or equal to x, we need to return the greatest value. So your task is to find the greatest value node of the binary search tree which is smaller than or equal to x. So suppose among all the nodes values, there are 5 nodes whose value is less than or equal to x. So among those 5 nodes, whichever has the greatest value, we will return it. Okay. Note, when x is smaller than the smallest node of BST, return -1. So basically, suppose the smallest value in the binary search tree is 7 and x is equals to 5. So there is no value which is less than equal to 5 in the binary search tree. So in that case, we will return -1. If we look at the example here, n is equals to 7, there are 7 number of nodes and x is 87. So what are the values less than equal to 87? 45, 66, 42, 87, 81 and 2. Among this, we need to return the value which is the greatest. So we will return 87. So the output will be 87. If we look at the second example, here there are 4 nodes, 6, 8, 7 and 9, and x is equals to 11. So what are the values less than equal to 11? 6, 8, 7, 9, all of them are less than equal to 11. Which is the greatest? 9. So we will return 9. Complete the function floor, which takes the integer n, that is the number of nodes, and BST binary search tree and an integer x, and returns the floor value. The constraints are given here. The expected time complexity is big O of n and expected space complexity is constant. So now if we think about solving this problem, then first of all, we need to understand the definition of binary search tree. So what is a binary search tree? First of all, it is a binary tree. It means that every node will have at max 2 children. So every node will have either 0 children or 1 children or 2 children. Okay. The second thing is that in binary search tree, the value of the parent node is greater than its left child value and the value of the parent node is less than its right child value, and this holds true for all the nodes present in the binary search tree. So 100 is greater than 90, its left child value, and 100 is less than 150, its right child value. Or you can also say all the values in the right subtree of 100 are greater than 100, all these values, and all the values in the left subtree of 100 are less than 100. Okay. Check for 90, 80 is less than 90, 99 is greater than 90. Similarly, 130 is less than 150, 170 is greater than 150. Okay. So this should hold true for all the nodes. First thing. Now, so what do I want? Suppose x is equals to 50 and this is the given binary search tree in the example. So we will start with the root node. We will be given the pointer to the root node. Now understand one thing. If at the current node the value is greater than x. So first of all, what I need? I need the greatest value among all the values which are less than equal to x. So first of all, if these are the values which are less than or equal to x, then among these, whichever is the greatest, I need to return that. Now if the current node's value is greater than x, then definitely the nodes in its right subtree will also have greater than equal to x value, right? So whenever a node has value greater than x, its right subtree will also have the values greater than x. So what we will do? We will come to the left subtree. Now 90 is greater than 50, so the nodes which are on the right subtree of 90 will also have value greater than 50 because these values are greater than 90, right? The right subtree nodes of 90 have values greater than 90, that is 95 and 99, and 90 is greater than 50, so these are also greater than 50. We do not want it, so we will come to the left. 80 is greater than 90, so we will ignore the right subtree of 80 and still come to the left. Now this is less than 50. So this is one of the possible answers. So what I will say? I will say answer equals to max of answer comma current node value, that is 20. Okay, and I'll initialize answer as -1. So answer is equals to max of -1 comma 20. So my answer will become 20 at this node. Now if a node has value less than or equal to 50, right? Then we will go on its right subtree. Why? You'll understand in the next step. So we come to its right subtree. Now again answer is equals to max of answer comma 30, because 30 is less than equal to 50. So this is one of the possible answers. So answer is equals to max of, what is the current value of answer? 20, and what is the current node value? 30. So it will become 30, right? Now understand one thing, 30 is less than equal to 50. Yes, out of all the possible values which are less than equal to x, we need to return the one which is greatest. Okay, now 30 is less than equal to 50. We stored 30 in the answer. Now the nodes which are in the left subtree of 30 will also have values less than equal to x, will also have values less than equal to 50. Agreed. But they will be less than 30, and we need to return a value which is less than equal to x, and out of all such values we need to return the greatest. So if 30 is less than equal to 50 and the nodes in its left subtree will also be less than equal to 50, but they will be less than 30. So among 30 and 25 my choice would be 30, because I need to return the greatest. So whenever I find a node's value greater than 50, I go in its left subtree like how we did here, because we can ignore these values. And whenever I find a node's value which is less than equal to 50 or x in general, then I will first compare it with the answer and then ignore its left subtree and go towards the right. Now 40 answer, now what will be the equation? Answer equal to max of 30, that is the current answer, comma 44. So my answer will become 44. Again I'll go to on the right subtree. Now what will be the equation? Answer equal to max of answer comma 51. But before making this equation, I'll check whether this node's value is less than equal to 50. This node's value is not less than equal to 50. So here I'll not apply the equation. And this is a leaf node. Its left subtree and right subtree both are null. So whenever I reach a leaf node, I'll terminate my process. And in this way, I'll get the greatest value which is less than equal to x. So just to conclude, I'll start with answer equals to -1, starting with the root node. If the value of that node is greater than x, I'll go to the left subtree. We can ignore the right subtree. If that node's value is less than equal to x, we will compare it with the answer variable and go in its right subtree to find greater value which is less than equal to x and update the answer if possible. And we will terminate when we will reach the leaf node. Now let's look at its actual implementation. So if we look at the actual implementation, so what I have done, I have initialized answer equals to -1. So why I have initialized it with -1? Because in case there is no value in the binary search tree which is less than equal to x, we have to return -1. So in that case, the default value -1 will be returned. Okay. So now we are at the root node. So while root is not equal to null, if the current node's data is less than equal to x, then update it with the answer and go on the right hand side. Okay, only if that node's data is less than equal to x. If it is greater than x, then go on the left subtree. Okay, so root equals to root left, and whenever root will become null, okay, at that time we will break out of the while loop and finally will return the answer. Okay, what would be the time complexity? The time complexity would be big O of n. Why? Because in case the binary search tree is leaned on one side. So what does that mean? Suppose my binary search tree is 1, 2, 3, 4, 5 and 6. This is also a valid binary search tree, and my x is equals to 6. So you come from here to here, then from here to here, then from here to here, and from here to here. There are n equals to 6 number of nodes, and you needed to travel all the nodes. Okay. So in case the binary search tree is not distributed and it is leaned on either the left or the right side, you might need to travel all the nodes. Okay. So in the worst case, the time complexity would be big O of n. And what would be the auxiliary space? The auxiliary space required here would be, see, we are taking only one answer variable. Okay, so it would be big O of 1, that is constant. Now let's submit this code. So let's submit it. So we have solved this question successfully. I hope you have understood the solution completely. Thank you.